In the last video, I talked a lot about function combinations, such as adding functions, the sum function, the difference function, subtracting two functions, product, and quotient function. And we got into little tedious details like domain and evaluating and so forth, and the idea. In this video, I wanted to talk about what we call a function composition and how that's sort of different than just a basic arithmetic combination of those functions. And also kind of talk about it conceptually. So I wanted to come to a metaphor that a lot of math teachers like to use, which we call the function machine, and kind of the idea of what a function does, and kind of use it to help understand the differences between function algebra and what we call a composition, which is just a different type of algebraic operation on functions, which actually does not exist with just basic numbers, and is unique to functions and other sorts of algebraic units, sometimes in math. But we can often think of a function kind of like a machine, where a function f, like I have my input x, which goes into the function, and what comes out is f of x, the evaluation. It's like I'm putting in a number, the function does calculations, grinds through that x, and comes out with, well, what is f of x? Is it x squared plus 5 or 2x minus 11? That is just dependent on whatever f is, and f is like the identity of that particular function. And we could then have g, which is a totally separate function, which takes the same input, grinds out something else. The sum function, which we talked a lot about the domain and stuff in the previous video, is a combination of those two. It's kind of like if I'm joining them together, creates a new function whose output is just equal to the net effect of those added together. It's not like you're not putting them together in some particular order. It's kind of like elaborating, creating a brand new function. And it's very different from transformations, because if I take a function and add another function, it's not just going to move it up or down, because that's what happens when I take a function and add 2, right? That would move it up 2, or f of x plus 2, in parentheses, would move it to the left 2. So basic adding and subtracting, that just moves the graph of the function around. When I actually add two of them together, it creates a whole new function which could look entirely different. It's kind of, there are ways to visualize what will happen, but it's no longer going to be a transformation because it's a combination of different functions, and that's going to be entirely different. So, like returning back to our function combinations, we can kind of use our functions to visualize this, and we did some examples in a past video. But again, the sum function would just be literally adding them together. And in the context of different algebraic units, like in this case, in order to actually add them, I could just leave it like this, but I could always form a common denominator and add it like this. And kind of the idea is this would be my sum function. It's a brand new function, which we would call f plus g, and it's not necessarily related to the originals, and it doesn't necessarily look the same. Or if I subtract them, it would be the same thing, but I would take the first minus the second. Again, I would need a common denominator to add or subtract with fractions. If I was going to multiply them, it would be a little easier, because if I'm multiplying a fraction by a whole thing, that always multiplies into the top, and it would give me this. And with division, I could use flip and multiply, which would give me this. But kind of the moral of the story here is I didn't want you to focus too much on the algebra. But basically, I'm getting a new function in each case, which is like the algebraic combination of the sum function, difference, product, and quotient. Now, a function composition is something that's different from that. And so that's the main thing I wanted to focus on in this video. And it's basically a new operation specifically with functions. And it's an idea of chaining two functions together. What happens if I apply a function, then apply another function afterwards? And that's different than adding them or subtracting or multiplying, because when you add, subtract, or multiply them, it does something new. It doesn't apply them successively. And we often refer to this as f of g of x for the combination of them in terms of a function composition. And so the definition of and we use the open circle, which is different than a closed circle, right? Because closed circle means multiply. Or if it was f dot g with a closed circle, that would usually mean the product function, which is the same as fg. But f open circle g doesn't mean the same thing. And I wanted to warn you about this, because every semester at least one student mixes this up with the product function, but it's not. It's something different. That's the whole point of this. Anyways, how we define what f open circle g means, or as we say f of g of x, is it means f of g of x. It's kind of like if notice that g function is on the inside of f. So instead of like plugging x plus 3 into f, I'm actually plugging an entire function into x. And that's the idea of how we actually evaluate and work on this. And also, if you were to reverse the order and do g of f, it would not be the same thing because they're not commutative. And we'll look at that as we work on our first example. And to sort of reiterate what this looks like based on the function machine metaphor, it looks like this. There's supposed to be an animation here, but it looks like it's not working. But I'll go ahead and try to draw it real quick. But let's say we were trying to examine a function machine where I'm chaining them together, as I said. So the little box will be my machine, the domain will be x, go in, and what comes out of it is f of x. But what I wanted to mention is how does a function composition work, is that if I first apply an input into f and then I send it through g after that, what would come out would be the composition of f and g. And actually, why I wanted to bring this up is what you might think is what this would be f of g. But actually what this makes is g of f of x. And I wanted to mention why it's backwards in the order of evaluation. And so again, g of f of x, that the definition of that would be g parentheses f parentheses x. And that's always what this circle means by definition. But notice, I want to talk about, well, why is g of f the order where I apply it first f, then g? And it's because if I think about the definition and how it's written right here, notice that f is on the inside. When I start with the domain into a function, parentheses always work their way inside out, right? So if I'm thinking about this, well, x is first being applied into f, because that's what f of x is, right? I would stick x into f, and what would come out is f of x. Now, after I figure out f of x, that would be this thing. Then now this is all within g. So it's sort of like f is being applied into g next, because really what comes out of this is not x, it's f of x. Then what I would get is g of f of x, because that's what's being plugged in for the domain. And that's why g of f of x first goes through f then g. And basically, one of the ways that you can remember this is kind of how I remember it, is that functions kind of get plugged in a backwards way, right? Because x goes into f, then f goes into g, which is why g of f of x conceptually would be the chain first into f, then into g. And as you could imagine, if we were thinking about f of g of x, that would be first into g, then into x. It would be a different chain because it would be a different order in which I'm applying them. So let's actually do an example of this, which there's one in the packet, but let's just look at the one in the slide similarly to before. So let's say we were looking at f of g of x. Again, by definition, that would be f circle g is defined to be f parentheses g of x. And how I recommend doing this is think about, well, g of x is this entire function in purple. So if I were to substitute that into here, this would be f of x plus 1. Or basically what that means is you want to plug in the entire algebraic function into f of x for x. Since this is f of this, which is x plus 1, I'm imagining that this is f of x plus 1, which just means I'm going to plug in x plus 1 for x. And my net effect of the composition, f circle g, would be this, which would be the chain of being sent through g first, then f. And again, we can see the value of this. And this isn't a very important idea for, say, computer science, where often in computer science, you're running programs, which is just sort of like, okay, if I start with something, I want to apply some sort of algorithm to it and come up with an answer. I could view a code or something like a computer algorithm as like a function where I have an input and an output. And I want to think about what happens if I apply one program, then I run the result through another program. It's sort of like the algebraic expression of the combination is the net result of doing both together in succession. Where again, if I were to run the programs in the reverse order, it might do something different to the outcome. And that's exactly what g circle f would be. That would be g of f of x, which would be what would happen if I take f of x, which is 1 over x, and plug that into g. Because again, f of x is this, so if I substitute that right there, I'd be doing g of 1 of x, which just means if I were to plug in 1 over x into g, that would go right here, and I'd be left with 1 over x plus 1. And as we can see, these are different because the location of the plus 1 has changed, and this is exactly why function composition is not commutative, because when I apply them in different orders, I get different results. Anyways, that's the basic idea. In the next video, I'll do another example from the packet of how to find what happens when you're composing functions together.